I wanted to show examples of finding derivatives of a function using both limit definitions of a derivative that we've discussed in class. So the first example here, I'm given f of x equals x squared plus 2x plus 5x plus 2. I want to find f prime of 2, so the derivative at x equals 2, using our first limit definition. And that limit definition is the limit as x approaches c of f of x minus f of c all over x minus c. Remember, the concept here is essentially that I'm finding a slope. And I'm finding a slope as my x values continue to get closer and closer together to that value at the point where I'm trying to find the derivative. So for example, we could find an estimation of the derivative by picking an x value of 2 and maybe an x value of something like 2.1 or 2.01 or 2.001. And the idea is, as that second value I pick gets closer and closer and closer and closer to the point at which I'm trying to find the derivative, I'm going to have my slope of my tangent, my instantaneous rate of change. At the point where those 2 points come together, I'm going to have the exact derivative. So I'm finding essentially my change in y over my change in x, my first point for x being that x value, my second point being that c value, and as that x coordinate approaches that c value, we're going to come together to get an exact derivative. So to follow the definition, I'm going to take f of x, which of course is x squared plus 5x plus 2. I'm going to subtract f of c. Well, my c value in this case is 2. So I can find f of 2 here. That is 2 squared is 4, plus 10, if I substitute 2 in there, is 14, plus 2 is 16. So it says I'm going to subtract that functional value. In this case, I'm going to subtract the 16, divide all of that by x minus whatever that c value is. In this case, this is 2. And I'm going to find the limit of that as I approach my x value of 2. So I can do a little bit of simplifying here. This is going to give me x squared plus 5x minus 14, appears to be what I have here, all of this, over x minus 2. Still finding the limit here. You'll notice, if I substitute in a value of 2 right now, I get a denominator that's 0. In fact, I get a 0 over 0 indeterminate form. So I need to try to simplify this down, write it in a different form. Notice that this factors. So I can find the limit as x approaches 2 of the factored form of this. We're going to get a quantity x minus 2 times a quantity x plus 7, denominator, still an x minus 2. And you can see that I can divide that x minus 2 out of both. And we end up finding the limit as x approaches 2 of a very simplified statement here. We're just finding the limit as x approaches 2 of x plus 7. Very simple at this point. I can substitute 2 in, because this is now defined at x equals 2, and we find out that our limit is equal to 9. So what this is essentially saying, when x is equal to 2, my derivative, my slope of my tangent line at that point, is equal to 9. Now I'm going to do the same problem as before, but I'm going to do it using our second limit definition of a derivative. This definition actually allows us to find a general equation for the derivative. And what that allows us to do is at the end we can substitute an x value in to find the derivative at any given point, instead of only being able to find it at one point like in the previous example. So actually what I'm really going to be doing here is I'm really going to be finding f prime of x, and then later we'll substitute 2 into this equation, and we'll see that we in fact get the same thing that we got using the other definition. The definition here is the limit as h approaches 0 of f of x plus h minus f of x all over h. This is what's referred to as a forward difference quotient. The idea being that I'm looking at 2 different points. I'm looking at a point where x equals just the value x, and then I'm shifting forward just a little bit, and we're having h represent that little bit that I'm adding to my x coordinate to pick my second point. Okay, so h might represent adding 0.1, might represent adding 0.01, some very, very small value that I'm going to shift forward to get my second point. I'm going to be finding the slope between the functional values generated by those 2 points, essentially, is what's happening here. So I'm taking my second y value, subtracting my first, So that's the change in y. And the change in x, I'm only moving over h units. 0.1, 0.01, 0.001, some very, very small value. So my change in x this time is really just that h value, and that's why I have that in my denominator. As that h value gets smaller and smaller and smaller, those points get closer and closer together, and they start to approach my actual derivative value. So as h approaches 0, if I can find that limit, I'm going to find my derivative equation. So we substitute in. This is a little bit messier than the other example. I'm going to find f of x plus h. Okay, so I'm going to substitute x plus h into this expression. So the original equation here, x is being squared, so x plus h is going to be squared, plus 5 times my x value. I'm going to be substituting x plus h into that as well, so 5 times x plus h, and then plus 2. So that is f of x plus h once I've made that substitution. I'm going to be subtracting the original f of x equation. So I'm subtracting this entire thing. Be careful here, use parentheses, or at least make sure that each value is being subtracted. Very easy to make a mistake on a sign here. Throw your entire derivative equation off. I need to expand this. Hopefully you can expand a perfect square very quickly and easily. If not, you can always use FOIL. I'm not going to show the FOIL here in this case, but this ends up being x squared plus 2xh plus h squared. Then I'm going to take 5 times this x plus h, so plus 5x plus 5h. Then I have my plus 2. Now I'm subtracting x squared. I'm subtracting 5x. And I'm subtracting 2. Right? What I should get here is a lot of cancellation. That's what I'm looking for. And so we can see in this case that the x squared values cancel. We can see that the 5x and the negative 5x cancel. And we can also see that the positive 2 and the negative 2's cancel. Now, I've gotten a little bit away in the process of trying to do some simplifying here. I've gotten a little bit away from my definitions. Let me go back here. It's the limit as h approaches 0 of that difference in f of x plus h and f of x all over h. So I need to write this back in a limit form to make sure that I'm still following the same definition. I need to find the limit as h approaches 0 of this simplified numerator that I found. And the numerator as it currently stands is 2xh plus h squared plus 5h. And my denominator here is just h. Well, right now if I substitute 0 in for h, you're going to see that everything here is going to go to 0. I end up with that indeterminate form of 0 over 0. I don't want that. So I'm going to divide out a greatest common factor of h from each of these terms. I'm going to end up with the limit as h approaches 0. In the top, I'm going to be left with a 2x. In the top, I'm going to be left with an h. And in the top, I'm going to be left with a 5. And there is no denominator now because I've divided out that h from the numerator and denominator. So that's what I'm left with. Okay? Well, still need to find the limit. Notice there's now only one h value left in this equation. So I substitute in an h value of 0. H goes to 0. That disappears from the equation. And I'm left only with 2x plus 5. This is my derivative value. This is my f prime of x. And that is my general derivative equation. If you want to check this, you can use the power rule. Okay, according to the power rule, I'm going to take 2 times my coefficient of 1, drop my power by 1, I get 2x. I'm going to take my exponent of 1 multiplied by 5, drop my exponent by 1, and I'm just left with a 5. So we can see that we do get the correct derivative here. Remember though, the original problem did not ask me to find the derivative function. It asked me to find the value of the derivative when x was equal to 2. Okay, so I can substitute in 2 at this point. 2 times 2 is 4 plus 5 tells me that f prime of 2 ends up equaling 9, which matches the value that I found using my other definition.